So our next talk is Proof Automation for Linearizability and Separation Logic by Mulder and Robbert Krebbers.
Yeah, thanks. So
Ike, sorry.
So what is linearizability exactly on these data structures? Well, we require that operations on these data structures appear to take place instantaneously, and that the effects of concurrently running operations always constitute some valid sequential history. And this is all kind of to say that the data structure really behaves like its sequential counterpart in the correct way. So if you have such a data structure and you want to establish this golden standard of correctness, what can you do? Well, people have researched this, and so there's various tools available. So I've listed some of them on the slides. There are more, and some properties of these tools. So for example, there's the Voila tool, which uses logical atomicity to establish linearizability. Logical atomicity itself is a compositional notion, and in the Voila tool you have some degree of automation in that you can write proof outlines and these are checked for you. And finally, the Voila tool is not foundational, meaning that you don't get an independent proof, unlike independent proof in a proof assistant, unlike some other tools out there. Now, another example is the Plankton tool, presented at OOPSLA last year, which really provides an impressive degree of automation, but the method they use itself is not compositional. So you'll notice that if you are looking for a compositional method of establishing linearizability, you're really not getting a lot of automation. Where if you choose a non-compositional method, you get a bunch more. And this is kind of a problem. So why do we care? What's compositionality even mean in this setting? So here we define compositionality as being able to use the linearizability of one data structure to prove that another data structure is linearizable. And this becomes relevant when you're doing large-scale verification efforts. And especially in these large-scale verification efforts, you really care about having some degree of automation. So that's kind of what this paper is about. What we do is we take two of these existing approaches of establishing linearizability and add automation to these systems. So we take the iris concurrent separation logic notion of logical atomicity and build automation for that, and the same we do for the ReLog system for contextual refinement. So that's the first contribution of this work. We provide proof automation strategies for contextual refinement and logical atomicity that can fully automate some simple examples, and for the more complicated examples, the automation makes good partial progress. And this is nice since it allows a style of proof of semi-automated. So you call the automation, it does some steps for you, it gets stuck for some reason, then you do some manual steps and then call the automation again. And the key ideas that allow this is that our proof automation strategy can use both the program under consideration and the logical state to determine the proof rule. And the second key part of these strategies is that they really minimize the amount of backtracking they do on proof rules. So this helps us with efficiency, of course, since the search space is smaller. But also this is really key for the partial progress part. Since as soon as you start backtracking on proof rules, partial progress kind of goes out the window since it returns either completely solved or no progress. All right, so contextual refinement, logical atomicity, these are very different notions, different rules and different strategies, but there's one thing which is quite the same, is that they both live in this concurrent separation logic. And so if you're building proof automation for these kinds of program specification styles, you really need to solve kind of the same problems. So you need to deal with separation logic bookkeeping, and since we're doing concurrent separation logic here, you need to deal with the challenges faced there, such as dealing with invariance and ghost state. Now to solve these challenges, we present our second contribution, which is Diaframe 2.0. So Diaframe is a proof automation library for Iris's concurrent separation logic. And the main addition with respect to Diaframe 1.0 is that it's now extensible with respect to program specification style. So previously we could just do Hoare triples, and now you can build your own proof automation strategy for the specification style you prefer. So in our case, this was a logical atomicity and contextual refinement. And here the key thing we discovered is that all the proof rules we kind of wanted to represent, they can be fit into one of two hint formats. So then the rules in a proof strategy can be represented in the Coq proof assistant as type class instances. So this makes it extensible and easy to experiment also with the strategies we tried. Now, for the rest of this talk, I kind of want to zoom in a bit on contextual refinement. What is that? And let's see an example verification with our automation strategy. So the data structure we will be giving behavior or specifying its behavior is a concurrent counter. So here, this expression on the slide will first allocate some location L, and then it will return a closure. And whenever you call this closure, it will use the fetch and add instruction to atomically increment the stored value in L by 1. Now, fetch and add will also return its old value. So whenever you call this closure, it will report to you how often this closure has been called. And so you can also call this closure concurrently and multiple times, and you can imagine using this in a kind of profiling system, for example, measuring how often a function has been called. Now, this data structure is linearizable since it always returns the correct amount of how often it has been called. And we will use contextual refinement to show that this is the case. So what is that? I've been talking about contextual refinement. We say that program E1 contextually refines program E2 for all well-typed context or clients C. If using the client with program E1 and this terminates with value V, then this is also a possible return value for when the client would use program E2. So clients cannot really tell the difference between these two expressions. And here the left-hand side expression we usually call the implementation and the right-hand side the specification. And this relates to linearizability in the following way. If we take E to be our concurrent data structure and we take the specification side, the right-hand side, to be a log-based sequential version of the same data structure, then this contextual refinement implies linearizability. So in the case of our concurrent counter, the log-based version is as follows. So we also allocate a reference, but we also allocate a log. And the closure we return in its body will first acquire the log, load the value, use regular load and store and increment in this critical section before releasing the log and returning the loaded value. So this is the contextual refinement we want to show. And now we will apply our proof automation strategy, which boils down for this example to these steps. So we do symbolic execution of the left-hand side, since these proofs kind of proceed by symbolic execution. So we do symbolic execution of the left-hand side until there is interference from some concurrent thread or the expression is fully reduced to a value. If we run into interference, there's a choice we need to make, and this is the source of backtracking that we do face sometimes, that we have to choose between restoring the invariant or doing symbolic execution on the right-hand side. And finally, once both expressions have been values, there is a value rule we should use to continue. Now, for this example, that's not relevant, and so it just becomes symbolically execute left-hand side, then right-hand side, and then use the value rule. So let's get started. The first thing we want to do is execute this allocation instruction, which returns some fresh x1, which we now know points to 1. So this is on the bottom left corner, we will show information we currently have about our heap. Now the left-hand side has been fully reduced to a closure, which is a value. And so we will continue with symbolically executing the right-hand side, which will also allocate a new location x2. So we have these two expressions, and so two kinds of points to. So there's an implementation points to and a specification points to keep them apart, since they kind of live in different worlds. And okay, so now we would need to allocate the log to continue, and now we need to think of the next thing to do. So both sides have been reduced to closures, which are values, and so we should apply the value rule. Now remember that these closures can be used concurrently and multiple times. And so if the closure has been called multiple times, we don't know that these locations still point to the value 1, since they can be kind of been incremented already. So the value rule for closures says that we must forget all the information we had about our current state. But we still have some information right now, and so doing that would kind of get us stuck. So at this point, the proof automation stops, since the value rule is not applicable. And this allows us to intervene now and do some manual steps in the proof. So what do? We squint at this, and this invariant inference is currently kind of out of scope for the automation. But we squint at this and we notice, okay, what keeps holding even every time we call the closure? Well, surely there's some number which these locations points to. And since we want to prove that these two closures can return the same value, we want to say that the actual values are the same. So this is, we generalize the current state of the heap to this, and then we say this is our invariant, which we will assume, or which we will show is enough to prove this contextual refinement. So we put this in a box and put it to the top left corner, where we will keep information which keeps holding throughout the execution. And at this point, you can call the automation again to continue. The value rule is applicable now, so we will enter the body of the closure and do symbolic execution again. Now we face the next tricky part, is that we need to show that this fetch and add instruction is safe to execute, which requires access to a points to, which we do not currently have in our knowledge about the heap. But by inspecting our logical state, we see that this points to can be found inside this invariant. And so the automation can figure out, hey, we need to apply some rule to open this invariant, get access to this points to again before proceeding. So we get to this state, and then we can symbolically execute this fetch and add instruction to increment the stored value and return to n. Right, so at this point, the left-hand side is the value, and we can do symbolic execution on the right-hand side, acquiring the lock, and doing the load and the store as the program says we should. And after releasing the lock, all we have left are two values to the equal natural numbers which refine each other, and we still need to restore in the invariant, but that's easily done, and so this concludes the proof. Okay, so the thing is, you don't want to do this manually, you want to automate this, and now you can. So the proof of this thing I just showed you becomes this proof in Coq. So we call the automation, that's the first line of the proof. This stops at the appropriate moment, allowing you to intervene and think of the correct invariant to continue. And finally, you call the automation to finish. Now, of course, this fetch and add instruction is a very simple example. What would happen more often is you have some kind of compare and set loop. But then if you do this, the proof remains exactly the same, since the automation can figure out, oh, hey, there's some induction step I need to do and apply, and that all kind of works out. What else is there? I described kind of the contextual refinement proof strategy here in the talk. In the paper, you will also find the strategy we have for logical atomicity. And we also describe the generic proof search strategy, which works in terms of the hints that we use to define these other two strategies. The paper also contains a more detailed evaluation, but I will give you some of that now. So to test this proof automation, what we did is we compared the proof burden for the automated proofs to some existing proofs, both done interactively for the RELOC framework. So those are contextual refinements, and they become about 7 times shorter. Also compared to the Voila tool for logical atomicity, their proofs become about 4 times shorter. And we finally redid some of the complex proofs done in Iris. Those also became about 4 times shorter. We also did some new results. So we showed the Michael-Scott queue to be logically atomic. This result is about 4 times shorter than an existing proof of contextual refinement done in CPP 2021. This kind of shows that with this automation, all these verifications become a bit more practical. So what I want you to take away here if you're doing proof automation in the setting where proofs are really hard and you cannot fully, completely solve them all the time, design proof automation that can make good partial progress. And a way to do this is by designing proof rules that don't look just at your program, but also look at the logical state in order to determine a good way to continue. With that, that's the end of my talk. One thing, I am looking for jobs in 2024, so this is interesting for you. Reach out.
All right, do we have any questions?
Okay, all right, the slides are gone. Can you tell me about the strength of the result that of the Birkedal et al. Refinement compared to the logical atomicity? Can you compare the strength of those two results?
Yes, so logical atomicity implies contextual refinement, and in the paper and the artifact we've actually used that to re-establish contextual refinement from the logical atomicity we've shown. So,
and the other way around?
That doesn't work. I think that logical atomicity is strictly stronger, but don't quote me on it.
Okay, thanks.
Very interesting and hopeful also. In one of your earlier slides, you showed many tools, and one of them was your work from last year. And your work from last year had dots to everything, as if it had it could do those proofs automatically. What have I misunderstood?
I think like the second slide I showed, maybe those didn't show any of my work, I think.
Okay, I have to ask you offline then. Okay, sorry. You have a slide where it says Voila plus my work in green.
Oh.
Something plus my work.
That's
and
yeah.
That's. It was last year, and last year could do everything.
So there was Iris and Relog plus my work, and what I presented last year, Diaframe, that didn't prove linearizability, and so it's not on the slide, since it could prove some properties of concurrent programs, but not linearizability, and that's what we're targeting with this work. But I can show you the slides, and you can show me where maybe I was confusing.
I had just one quick question, which is you use hints to direct the automation in a particular direction. Does it ever happen that those hints are wrong? And what do you do then? What does the user do?
So when I as a strategy designer create wrong hints, I should of course create better hints. If the user tries to write hints themselves and then figures out they are not the right way to go, so then the proof automation will take a wrong step. What you can do in this case is say, hey, proof automation, only do X many steps, and this helps in kind of figuring out where it went wrong, and also allows you to intervene if you want to do something else in a particular case.
All right, thank you. All right, let's thank the speaker again.